Hey guys, in this video, let's talk about ensemble learning methods. We'll go over 3 common types of ensemble: bagging, boosting, and stacking. Here are some interview questions. What is ensemble learning? What are the examples of ensemble learning? What are boosting and bagging? What are the advantages of bagging and boosting? What are the differences between bagging and boosting? Why boosting models are good? Explain stacking. As you can tell, being able to answer these interview questions requires you to have a clear understanding of different ensemble learning methods. So in this video, we'll go over all of them, and let's start with understanding what is ensemble. The idea behind ensemble method is pretty simple. It's that a group of weak learners can come together to form a strong learner, and the strong learner will have better predictive performance than could be obtained from any of the base learners alone. If one base learner is erroneous, it can be auto-corrected by others. So the final model is typically less prone to overfitting and more robust. It's unlikely to be influenced by small changes in the training data. Here's a diagram showing the concept of ensemble for classification tasks. We start with the training set. Then we build classification models based on this training set. We have M models in total, C1, C2 to CM. And then each model has its own predictions. And then we look at all these predictions and we use voting to output the final prediction. Voting means that we select the most frequent results across all these predictions. Now we know the general idea of ensemble. Let's look at one ensemble learning method, bagging. Bagging is short for bootstrap aggregation. It builds several instances of an estimator on bootstrap samples of the original training data and then aggregate their individual predictions to form a final prediction. Here's a diagram showing how it works. The first step is to create bootstrap samples, sampling with replacement from the training data. Here we have M bootstrap samples from T1 to Tm. The reason we create bootstrap samples is that we want to ensure each sample is independent from others, as it does not depend on previous chosen samples when creating bootstrap samples. Then we use a single learning algorithm to build a model using each bootstrap sample. These models can be built in parallel. As you can see, we have C1, C2 to CM, M classification models in total. Then we use multiple models to make predictions, and the predictions are combined using voting or averaging. This diagram shows bagging for classification tasks, so it's using the voting method. Voting means that the most frequent result will be the final prediction. And averaging for regression tasks means that we want to take the average of all these predictions to be the final prediction of the model. An example algorithm leveraging the bagging method is random forest. Here's how it works. Random forest combine a set of decision trees to make predictions. Decision trees are good candidates for bagging because they can capture complicated interactions in the data, and if grown sufficiently deep, they have relatively low bias. Because trees can be noisy, they benefit greatly from the voting or averaging method to get the final prediction. From a bias variance trade-off point of view, random forest starts with low bias and high variance, because its tree is fully grown and decision trees tend to overfit. And then the random forest work towards reducing variance by taking majority vote or averaging across trees. Alright, now let's move forward to boosting. Boosting improves the prediction power by training weak learners sequentially, each compensating the weaknesses of its predecessors. Let me explain what this means. Boosting starts with a weak learner, gradually turn it into a strong learner by letting future weak learners focus on correcting mistakes made by previous learners. For example, in classification tasks, misclassified examples gain a higher weight than examples that are classified correctly. So future learners focus more on examples that previous learners misclassified. So essentially, we are making the weak learner more complicated, and this process will help reduce the bias of the weak learner. Here's a diagram showing how it works. Boosting starts with a weak learner, better than random guess. You can see that in the first iteration, some examples are classified correctly and some are not. In the next iteration, the weights of the data are readjusted so that they can be corrected. Boosting assigns higher weights to those that were classified incorrectly and lower weights to those that were classified correctly. This sequential process of giving higher weights to misclassified predictions continues until a stopping criterion is reached. And the final prediction is the weighted result of all weak learners. One popular example of boosting method is gradient-boosted trees. Gradient-boosted trees train decision trees sequentially. It optimizes the residual loss of a tree by adding another tree. It appears to outperform bagging on lots of problems and become the preferred choice. From a bias variance trade-off point of view, gradient-boosted trees start with high bias and low variance because the first tree is shallow. It's slightly better than random guess. And then they work towards reducing bias by making the tree more complicated. Now let's summarize the differences between these two ensemble learning methods, bagging and boosting. In bagging, individual learners are trained independently. They can be built in parallel. Versus in boosting, individual learners are dependent on each other. Remember that a new learner is created to correct mistakes of the previous learner. So the process is sequential. From a bias variance perspective, bagging reduces variance of individual learners, while boosting reduces bias by making individual learners more complicated. Because of this, bagging methods work best with strong and complex models, for example, fully developed decision trees, while boosting methods usually work best with weak models, for example, shallow decision trees. A good example of bagging is random forest, and an example of boosting is gradient-boosted trees. Finally, let's look at stacking, another ensemble learning method which is less frequently appears in interviews than bagging and boosting. The idea of stacking is to build a meta model that takes the output of base learners as input. It combines estimators to reduce their biases. It can be applied to classification and regression tasks similar to bagging and boosting. Here's a diagram of stacking, and we can consider it as two-level ensemble method. In the first level, individual estimators are created based on the training data. Here's a diagram showing how it works. We can consider stacking as two-level ensemble learning. In the first level, individual estimators are created using the training data. And then a combiner estimator or meta learner is created to fit to the level 1 estimator predictions to make the final prediction. For example, a stacking model for classification tasks can look like this. The individual classifiers are random forest and support vector machines. And then we have a meta learner or stacking classifier, which is logistic regression, to make the final prediction based on the output of individual classifiers. The stacking method has some pros and cons. In practice, a stacking predictor predicts as good as the best predictor of the base layer and sometimes outperforms it by combining the different strengths of these predictors. But training a stacking predictor is computationally expensive.